Hello, we hope everybody's having a great day and staying safe. We are RL Squared Engineering from Tarleton State University, and I am Wesley Lozano.
Josh Ringo.
And Shannon Lawless.
This is our presentation for the Water Environment Federation's annual Student Design Competition. Our design is for improvements to the central wastewater treatment plant in Pflugerville, Texas. Our team was tasked with creating a three-phase design that will accomplish three main objectives: expand the plant capacity to 10 mgd, convert from chemical to biological phosphorus removal, and upgrade the existing sludge handling facilities. In total, we developed and evaluated three design alternatives. These alternatives will be presented in the following slides. Here's a quick overview of the existing site layout. As you can see, there's plenty of room for expansion of the facilities.
This is an existing process flow diagram. As illustrated, the water enters the plant through the Archimedes screw pumps just before it contacts the screens. From there, the wastewater flows into the aeration basins where it is mixed using mechanical aerators. Then the wastewater flows into secondary clarifiers before entering the chlorine disinfection chamber. After disinfection, the wastewater enters tertiary filtration before flowing through a post-aeration basin and leaving as treated effluent either to a nearby stream or as reuse water.
This is a brief overview of the existing plant. It was designed in 1986 to handle 3 mgd, but was reevaluated in 2016 to reveal a capacity of 5.3 mgd. Currently, the plant is at 75% capacity and is expected to reach 90% capacity this year, which, according to TCEQ, is a threshold for initiating the design of expansion.
This table includes characteristics of each facility and several process components, as well as vital information in evaluating the treatment capacity of each facility, so that we could determine the extent of expansion required to reach 10 mgd. The scope of this design project includes curating a preliminary engineering report and presentation that provides a qualitative and quantitative design assessment for multiple alternatives, as well as a comparison of these alternatives to arrive at a recommendation. Each alternative ultimately must be designed to be implemented in 3 distinct phases. Phase 1 being a comprehensive capacity expansion to 10 mgd, be completed by 2021. Phase 2, a conversion from chemical to biological phosphorus removal, to be completed between 2022 and 2023. And Phase 3, including general upgrades to the solids handling process, to be completed within the next 7 to 12 years.
There are 3 major factors when defining the design criteria. These are state-specific, such as influent wastewater characteristics, and TPDES discharge permit limitations or client requests. Many of the client requests have already been mentioned in the project scope. Some that have not been mentioned but were also considered were odor control due to the proximity of the site to a local park. Additionally, TCEQ requires standards to attain the Type 1 and 2 wastewater reuse currently practiced at the plant. Some more general considerations made in the design include the environmental impact, operational ease, and safety hazard minimization. These tables shown represent the wastewater influent characterization. The parameters given in these tables are essential for the theoretical design of the wastewater treatment facilities. However, due to the unavailability of other important data for sizing, various assumptions also had to be made in the design process. This table depicts the TPDES limitations necessary to satisfy the TCEQ requirements. The capacity expansion for the plant warrants an update to the permit. However, with all else equal, the only change in limitations is with regard to the average flow of effluent discharge.
Now we will discuss the recommended improvements, starting with those that will be implemented in Phase 1. The headworks facility is currently unable to handle peak flow conditions of 35 mgd and therefore requires capacity expansion. Starting with the influent lift station, the existing Archimedes screw pumps are large and energy intensive, and to add more would require a more construction than converting to a submersible pump skid. For that reason, our design includes a new influent basin with 4 submersible pumps, one of which will be held on standby to be used in the event that one pump requires maintenance. The capacity of the screening facility will be doubled by adding 2 screens of similar specification to the existing, constructed such that the entire facility will share an influent channel separated from each screen channel by gate valves to give the operators complete control over the flow. During our site visit, we learned that the plant experiences a great deal of sediment buildup that plant staff have to manually shovel out on a regular basis. To prevent this in the future, we are also including a grit removal cyclone following the screens, complete with a bypass channel to keep the plant operational if the cyclone requires maintenance. The size requirements for the oxidation ditch expansion in Phase 1 were based entirely on the demands of biological phosphorus removal, which will be implemented in Phase 2. This eliminates the need for unnecessary construction costs of resizing the facility twice, and to ensure redundancy in the system, 2 additional basins will be included. The design for Alternative 1 is based on a traditional A2O process, which keeps the existing facility design MLSS of 3,500 milligrams per liter, requiring a total volume about 4 times of what the existing ditches offer. Alternative 2 includes the same A2O process, but with the addition of an integrated fixed film activated sludge media, like that shown in the bottom left picture. This design allows the design MLSS to remain at 3,500 milligrams per liter, while increasing the effective MLSS to 7,000 milligrams per liter. This eliminates extra solids loading to the clarifiers and reduces the required volume evaluated in Alternative 1 by 60%. Alternative 3 again incorporates the A2O process, but includes granular activated sludge produced by a hydrocyclone assembly. The granular sludge allows us to operate the plant with a design MLSS of nearly 12,000 milligrams per liter and still does not add any extra stress to the clarifier since its settling velocity is so much higher. Alternative 3 ultimately reduces the volume requirements evaluated in Alternative 1 by 85%.
Currently, the plant has 2 secondary clarifiers, both 115 foot in diameter. For the purpose of land availability and uniformity, our designs for the oxidation ditches in each alternative are based on the addition of a single clarifier, also 115 foot in diameter.
One of the goals we set out for our design was to eliminate gaseous chlorine from the plant to reduce the risk of a hazardous event affecting plant staff or the surrounding public facilities. The method we chose was closed vessel UV disinfection because of its small footprint, ease of implementation into plant hydraulics, and its environmentally friendly nature. UV, however, is not a TCEQ-approved disinfection technology for reuse, so sodium hypochlorite will be used to attain a chlorine residual in reuse water and to prevent bacterial and algal growth on weirs and in splitter boxes.
For tertiary filtration, we needed to bring the plant from where it is currently at 16 mgd peak flow to 35 mgd peak flow. To do this, we evaluated a couple of alternatives. We looked at both inside-out and outside-in filtration and compared the two based on their respective costs, ease of implementation, and space requirements. Looking at these 3 parameters led us to the recommendation of the Aquadisc with Optifiber cloth media by Aqua Aerobic. This system has an outside-in configuration and will integrate easily within our current system, which is also outside-in. Regarding post-aeration, at the moment the system in operation at the plant consists of 2 blowers capable of producing 110 standard cubic feet per minute each. We are recommending that the blower installation used for the A2O process also be used to supplement the needs of post-aeration. This reduces cost and maintenance from having 2 new separate systems.
That is the extent of our design for Phase 1. Now we will move on to the conversion from chemical to biological phosphorus removal. To incorporate the A2O process into the plant for each alternative, the oxidation ditches have been sized to prepare for a retrofit during Phase 2, meaning no additional basins are required. This retrofit includes installing baffle walls to the oxidation ditches to create distinct anaerobic, anoxic, and aerobic zones. These existing basins will have supplemental diffused aeration discs installed, while the new basins will have their aerobic zones entirely fitted with these discs. To ensure each existing basin could retain their mechanical aeration components and flow direction, the effluent weirs and influent piping will be moved as illustrated in the drawing on the left. In addition, the return activated sludge piping will be rerouted to the influent of the anaerobic zone, and an internal recycle feed from the aerobic to the anoxic zones will be included.
Alternative 2 includes the integration of IFAS into the aerobic zone of the A2O process. The company who designed the original basins, Ovivo, also manufacture rope media IFAS units that can simply be lowered into the basin from above without any additional construction. The media creates an environment that introduces an additional 200 or 2,500 milligrams per liter of fixed MLSS on the ropes without sending it to the clarifiers.
The use of granular activated sludge in a continuous flow treatment process is still a new technology. However, it has seen great success in several treatment plants and pilot studies. This process is implemented using the indents hydrocyclone, which separates the denser from the less dense sludge, and only sends the denser sludge back as a RAS feed. This allows the sludge to granulate over time, and each granule develops its own A2O treatment zones, as shown in the figure on the bottom right. Not only does this amplify the treatment capacity of the activated sludge process, but the dense sludge settles exceptionally well when compared to normal sludge. Perhaps the most attractive characteristic of this alternative, implementing granular sludge for 10 mgd of average flow requires only a small assembly of 2 hydrocyclones, about half the size of the skid in the top left picture.
Finally, the Phase 3 implementations recommended will be discussed. The main solids handling improvement is the addition of an anaerobic digester, which will be discussed more on the next slide. However, allowing the sludge to enter anaerobic conditions will trigger a secondary release of phosphorus. If this occurs, it will decrease the phosphorus removal efficiency. Because of this, an appropriate thickening process before anaerobic digestion is necessary to prevent this release and improve overall digestion yield. To ensure efficiency in digestion and phosphorus removal, 2 3DP gravity belt thickeners will be installed in parallel. The flow entering the gravity belt thickeners will be roughly 340 GPM, assuming that the flow simply doubles with the increased design flow of the plant. After thickening, the volume of sludge entering the anaerobic digester will be significantly reduced to roughly 57 meters cubed per day. The anaerobic digester was selected as the main improvement because of the positives that come with it. This will help odor control, reduce the volume of disposed sludge, it could allow the sludge to be used for other reuse purposes in future projects, and most important, harvest energy in the form of methane that will provide an additional source of income for the plant. The new solids flow rate after the thickener indicates that, assuming a retention time of 10 days, a total volume of 572 meter cube would be needed for the anaerobic digester. The digester will be an enclosed concrete structure constructed with Enviromix air burst mixing, an air mixing system that uses inert gases that won't hinder the anaerobic process. With the expected volume of the sludge at a temperature of 35 degrees Celsius, a total of 1,088 meter cube per day of methane gas will be produced. The following slides will include our official design recommendations for the plant. This decision matrix gives a breakdown of how we compared each alternative using the criteria we felt were the most important for the plant and to the client. We compared overall capital cost, operation and maintenance cost, ease of implementation, and land space requirements. While we predict alternative 3 to be marginally more expensive to operate, it is clearly the most feasible to overall, and has ultimately earned its spot as our recommendation.
This is the process flow for the plant with our recommended upgrades implemented. A few of the noteworthy changes are the addition of grit removal and the A2O modifications, as well as UV disinfection. The additions to the sludge handling facilities are also shown by the hydrocyclone, gravity belt thickener, and anaerobic digester.
Based on our head loss calculations, the plant theoretically should function without any hydraulic interference. Here is the hydraulic profile for the recommended improvements from the headworks through the clarifiers. And this is the section of the hydraulic profile from the effluent of the clarifiers through the plant's outfall.
Here's a conceptual overview of the recommended site layout to help visualize the land space requirements. You can see the Phase 1 improvements in green, Phase 2 in blue, and Phase 3 in red. For our recommended alternative, we came up with an opinion of probable construction costs. For this estimate, we drew information and prices from our advisors at Garver Engineering and from the RS Means Cost Estimation Manual. With the final cost, we included 2 contingencies, 30% for unknown costs for electrical and other site work, and 5% for any other miscellaneous items. Our final project total is estimated to be $30,591,000. Here are our references.
Last but not least, we would like to thank Dr. Kartik Venkataraman for serving as our faculty mentor at Tarleton, Tina Hansen from Garver for being our professional mentor for the competition, and the Water Environment Association of Texas for giving us the opportunity to be here. Thank you very much and have a great day.